one, we have Sabrina Pasterski on some formal development on scattering amplitudes, so applying lessons from holography and conformal theory to scattering.
Hello, hello.
We can see your slides.
Awesome. Yes. Great. So thank you guys for having me. It's very fun to be talking to a nice broad audience about some research work that's kind of come out of Strominger and others out of Harvard, starting maybe 5 or so years ago. And we're building up a framework to try to kind of rewrite S-matrix elements in terms of correlators on a CFT. And so that's what we'll be talking about today. Great. Okay. So I guess taking a step back to some of the original motivations, we'd like to kind of tackle some interesting fundamental questions, like what are certain consistency conditions we can impose, what happens at energy scales we can't yet probe, and then other fun thought experiments. And typically the way that we do that is we would try to say like, okay, like is our theory consistent? What self-consistency conditions can we impose, and try to go as far as we can theoretically without necessarily always having experiment to back us up. With ideally the feedback loop, then updating our consistency conditions. So as a high energy theorist, like the best puzzle, like our gap in our understanding right now is the fact that we know that we should have a consistent theory of quantum gravity. So at short distance scales, everything should be quantum mechanical, but at large distance scales, we want to reproduce general relativity. And if you just try to treat it in like the standard quantum field theory way, you run into a bit of issues. First of all, like that the theory would be non-normalizable, that if you treat a curved background and then quantum fields on top of it, you've run into various issues like the information paradox for when you think about a black hole evaporating, as well as other problems when you fall in through the horizon, even though you think that the curvature scale would be such that everything should be fine. So the approach that I'm going to be talking about today is trying to kind of take it from a different direction than maybe what a standard high energy theory approach would be. So typically, maybe like what the people who get into string theorists would be considered as saying, okay, well, we know that treating it as a quantum field theory is a problem. And so at some higher energy scales, we need to have a different framework for describing the same interactions of particles in a series of particles. So instead of having these world lines, they turn into world sheets. And so you would think of like, okay, let's find some self-consistent description of this UV physics and then see what it tells you about physics at the energy scales that we probe. And that's a very fruitful, like swampland style approach. And then the other route would be to try to go all the way back to the infrared. So say we know that we're in 3+1 space-time dimensions. We know that basically at very large scales, the cosmological constant is very small. So can we use the symmetries that you'd have in that background to highly constrain the quantum gravitational S matrix? And so that's the route that we're kind of following, but of course, inspired by the fact that this theory has to be consistent at all scales. So on the one hand, this is like looking for string theory. On the other hand, is trying to use Noether's theorem as much as possible. Okay, so today what I want to introduce is basically a framework that's trying to reorganize the scattering problem in a manner that will show or make manifest an infinite dimensional symmetry enhancement. And I'll start with middle of the talk will be focusing on where you can get more symmetries from. And then the second aspect of it is that by taking seriously the fact that you want to use these symmetries to the fullest extent you can, you end up recasting these S matrix elements in terms of this effective conformal field theory. And then hopefully you can try to learn about amplitudes using conformal field theory techniques. So that's what we're going to close on, and also the title of the talk. Okay, so where are we even coming from? So the kind of core notion is that if you have a quantum gravitational theory, that it's somewhat intrinsically lower dimensional. So there's a theory that is lower space-time dimensions that doesn't have gravity and that captures the same physics if you know how to write a dictionary between the two. So the first kind of evidence or example of that is the manner in which a black hole will behave like a thermal system, where basically the entropy scales like the area as opposed to the volume of the system. So there's already something kind of hinting at that with Bekenstein and Hawking. And kind of the canonical success story for the last, I guess, since the late 90s is ADS CFT. So anti-de Sitter space, quantum gravity and anti-de Sitter space being dual to some conformal field theory that's living on the boundary. And the notion of that duality is important for a couple of reasons. So first of all, you actually have a string theory realization of this equivalence. And then kind of the way that it evolves over time is that it becomes this toolkit for both high energy theory and condensed matter experiment or theory, and then also some applications to quark gluon plasma physics. So there, if you say that there is an equivalence between something that's happening in this now curved, maybe somewhat unphysical background, and a conformal field theory, in that example, there's things you can compute on either side, which are easier to compute on one side than the other, often because this is strong weak duality. And so then you can see where something would be very difficult to compute on one side of the duality, but you have this equivalence, then you can use the easier tools on the other side and pretend that it's a conformal field theory as opposed to a quantum theory of gravity, or pretend it's a gravitational system as opposed to a conformal field theory, and learn on both sides. So the ideal here, like the gold standard, is that you have a intrinsic high energy theory description, so the stringy realization or whatever, that lands you on this duality, and then that the nature of that duality is such that you have two uses for it, like both a boundary use and a bulk use of it. So bulk, I mean this interior here. So what I will be talking about today is trying to kind of use that paradigm, that the fact that you have some sort of holographic dual of scattering in a different background, to try to push and set up the start of that duality. But there's a lot to grow from there, where you want to really be able to use it to your advantage, as opposed to just in one limit where you know the bulk theory as being this perturbative field theory. Okay, good. So ideally you have this great example of something where we've learned a lot from it over the past couple of decades, and you want to then apply it to astrophysically relevant context. So the first negative, I said some positives of this ADS-CFT correspondence, is that it's in ADS. It's not in de Sitter. It's not in even Minkowski space. And so the fact that the cosmological constant is the wrong sign is not good for trying to say that, okay, this theory is a dual to everything in my universe. But on the upside, there are ways to kind of make some approximations where it is an interesting model. So for instance, if you were looking at a rapidly rotating black hole, then there's a region of the geometry, in this near horizon region, where you can model it by effectively, one of the factors of the geometry is an anti-de Sitter spacetime. So Kerr CFT was an effort to try to take advantage of that gravity and CFT duality to kind of learn something about what's happening during the photon ring here. And so some people are actually trying to then see if they can use those conformal symmetries to say something interesting about the signals that you would see when you're looking at the Event Horizon Telescope. So that's fun. So there are ways to, aside from also this quark gluon plasma example I was mentioning, to try to take advantage of the standard version of ADS-CFT in astrophysical context. Of course, if I want to talk about space-time at a very large scale, I need to not ignore the cosmological constant. And so I'd want a de Sitter CFT correspondence, and so there's been work along those lines. And the thing that I'm going to focus on today is kind of the intermediate range of scales, which is a very large range of scales. So I could pretend my space-time is actually just flat. So lambda is 0. And I basically, when I make that assumption, I can actually kind of talk about gravitational radiation coming from inspiraling binary systems, or even down to looking at scattering processes at the LHC. So there's a long range of scales for which it's approximately valid to say that the background spacetime is flat, and then go on forth and try to find a holographic dual description of it to describe those types of interesting scattering experiments that can happen at those different ranges of scales. Okay, so then that gets me to this program that I'm very happy to be talking about today. So celestial holography, in quotes, is this purported duality between gravitational scattering and what I'm going to introduce as asymptotically flat spacetimes, and a CFT that's living on the night sky, basically. So you look up at the stars, you're seeing light coming to you from those stars, so that's going to be the celestial sphere. And of course, there's also the time coordinate that you're seeing light emitted at different times. So that's infinity. Celestial amplitudes for us are going to be S matrix elements just in a basis where they then transform these correlators. So the central object of study then is the S matrix in that basis. So this S matrix, I prepare some initial states and some final states and ask what's the likelihood of scattering between those two. So the point is that for me at very early and late times, I have these on-shell particles, and there's some quantum mechanical theory of gravity, hopefully, that governs the interactions here. And the point of this program is to then map that over to a set of correlators on this night sky that are going to tell you then not necessarily just one scattering process, but kind of some integrated sum over scattering processes. And so that's going to be the point of this talk today, to introduce why we would want to do that, and some of the results that come out of doing that. Okay. So very first step, if I tell you that everything you're talking about with these like S matrix elements can be written in terms of a conformal field theory of the celestial sphere, why is it a conformal field theory as opposed to, so conformal means I can basically like only need to look at angles and not preserve distances. So this like warping of the geometry happens even if you just think about like boosting in a given direction. You're going to see the stars in the night sky move around in a manner that would match a conformal transformation on the night sky. So Lorentz transformations in Minkowski space are acting as global conformal transformations on the celestial sphere. But the fun thing about it is you don't just have global conformal transformations, you don't just have Poincare, you actually have a much larger set of symmetries that are realized non-trivially in scattering matrix elements. So if you say I'm going to look at spacetimes that are vanishing cosmological constant, that doesn't mean actually just Minkowski space. You don't want to just think about this, nothing's on my spacetime. You want to be able to basically add in matter. So think of like a solar system or galaxies or whatnot, but no cosmological constant. And so for certain assumptions on the types of matter that you're allowing when you're trying to solve Einstein's equations, like there's going to be a certain larger class of spacetimes, which I will call asymptotically flat. So basically localized stress tensor sources, vanishing cosmological constant, and Bondi, Vandenberg, Messer, and Sachs in the 60s were studying this and explaining how to, I guess, quantify the metrics that would correspond to this class of solutions. So while the metric on the left has basically non-trivialized symmetries, you have the Poincare group there. Once you start adding more complicated matter distributions, even though in principle, like the space-time background is like somewhat the same, that metric itself does not have those isometries. And so it would be a pity if you kind of lost the point of like even Poincare invariance, because now your background, it has like some stars sitting there. Like you want to be able to use, even like in daily life when we're like doing high school experiments, we have the translation invariance talking about how billiard bars are going to interact, and it doesn't care that like that basically overall like you don't actually have that isometry of the background. So what for the technical purposes of looking at S matrix, like these extra symmetries that you get are going to be called asymptotic symmetries. And so what they are is basically, I go very far to basically infinity, and I look at how does my metric behave. And I try to gauge fix in a manner that then sets it up so that I have a well-defined initial and final like value problem. And then I look at this kind of the space of solutions. So basically, I want to capture the free data for the metric is going to be this spin-2 radiative field. And like Bondi, Vandenberg, Messer, and Sachs knew how to, like that would be encoded in the subleading term in the one of our fall-offs of the metric at infinity. And then what happens is you have this game that you're playing. You're basically saying like, well, I don't want to allow like something that's going to radiate forever. I want to have some sort of physical notion of what the behavior along time and at large distances should be for my metric. And then also, so once I start to set that, then I would have extra gauge symmetries that basically are keeping me within those boundary conditions. And so one can see that basically there's this trade-off between what fall-offs, what assumptions I make about the behavior of the fall-offs, and then what extra symmetries I have to then move me around within those sets of fall-offs. And so it's a bit of a balancing act. But the funny thing about it is that through the balancing act, you don't just land on Poincare, you're always stuck with something larger. And so what I'm going to call the asymptotic symmetry group is those sets of residual diffeomorphisms, or also gauge transformations as the analog for a spin in one, that basically will act non-trivially at my initial and final data, but will be in some sense like allowed because of the fact that they're keeping my metric within the given boundary conditions. And so the fun thing about that is it's much larger than Poincare. So you have infinite number of symmetries as opposed to just your 10 generators of Poincare. But generically, your asymptotic symmetries are going to be much larger than global. And basically, you have then some low energy modes corresponding to the spontaneous breaking of your asymptotic symmetries down to your global symmetries for a given vacuum. So this structure is a paradigm for moving me towards celestial holography, as I'll get to next. So basically, what do I actually get if I repeated the exercise on the metric as I wrote it out? You get two things. You get the ability to basically time translate at different points in the night sky independently, as well as do boosts in different directions. So one thing that if someone is in like jet phenomenology might remind them of is the ability to basically like look at different reference like coordinate frames for like the amount that you're going to like boost a jet. So if you try to set a tetrad around a given jet direction, the freedom that you have in picking that is related to these super rotations, because basically I am allowed to kind of match what the Lorentz transformation would look like near any different point on the night sky with these guys. And the cost that you pay, of course, is that it's not a standard symmetry in the sense that I I rearrange all of my charged particles and then it's conserved. I actually have to add in some soft radiation. And so the fun thing about this is that it basically is deeply connected to just like the fact that there are certain low energy observables and constraints in your system. So I mentioned this asymptotic symmetries as a motivation to say like why using a framework where you put the symmetries first can get you more because there's more symmetries. But it's also, there's also feedback with some experiment in the sense that I can go out and I can try to measure the corresponding observable that is basically canonically paired to the symmetry generator. And if I see that, it feeds back into whether or not I have that asymptotic symmetry as something that's relevant for my spacetime. And the way that it's realized in the S matrix elements is via soft theorem. So basically, the symmetry point of view is I'm just looking at my the data that describes my field configuration at very early and very late times along like a null notion of infinity. And that the fact that that is also actually realized in my S matrix elements, so it's already there, is kind of nice. And it's there via quantum field theory soft theorems. And so it makes sense from the point of view that something at long distances should be low energies. But perhaps it's non-trivial that basically the identity that is the soft theorem is actually equivalent to the asymptotic symmetry. So that recognition was something that Strominger was noticing and kind of pushed this direction. So basically
you have 8 minutes.
Perfect. Yeah. So basically, this is a template for finding the new iterations of this. So basically, in some examples, it was from the 1960s that Weinberg studied his original soft theorem, that the asymptotic symmetries were studied by Van den Berg, Metzer, and Sachs, and that Zoldovich and Polnareff and others knew about memory effects. But the fact that they were all interconnected was something that was appreciated like recently. And the fun thing about it too is that when new physics from the point of view of like not like new particles, but new universal subleading soft theorems, et cetera, can be identified by knowing that you know one of the examples here and not the others. So that was what happened with spin memory. Basically what would happen is you have some inspiraling binary system, it's emitting gravitational radiation, and it would be kind of strange if that radiation had a non-zero, had a zero time integral in some sense. Like you have this energy flux coming out, angular momentum is being lost. And if you can measure the net amount, so the time integral of that radiation, those zero modes are the memory effects that I'm talking about. And it's constrained basically by these symmetries to be related to the initial and final kinematics of the system. And so that's the thing that you would measure to then try to see if the proposed extension of the symmetry group is there. Again, the soft theorem issue is deeply tied to issues of IR divergences. So on the one hand, when I want to prove my ward identity, I'm just using the fact that if I add an extra low energy particle, it's proportional to the amplitude without it. But more interestingly, perhaps at least from the point of view of defining physical quantities when I'm talking about like comparing my S matrix computations to something I would go measure at CERN, the issue of IR divergences is a problem because typically you would exponentiate exchanges between these charged legs and you'd find zero. And then the standard workaround in the quantum field theory textbooks is that, okay, no, I really didn't measure everything below a certain cutoff. So I can't measure these zero mode guys. And therefore, like, I should really be summing over the things that I can't measure with my detector, and then it's fine. Understanding that that divergence is coming because you aren't satisfying the constraints gives you more freedom to understand how you want to dress the particles. You don't have to dress like the in state and the out state. You can put the dressing for the in particle in the out state, for instance, and still satisfy the constraints. So these symmetries are connected to that and give a different understanding. And then on it, from the point of view of the different quests that we had, the fact that you have an infinite number of symmetries can just be applied directly to other interesting problems. For instance, someone falling through a black hole, there should be contributions to the charges from both asymptotic infinity and also the horizon. And so you have these constraints applying to black hole evaporation and infallers, et cetera. So the power of symmetries is vast. For the point of what I want to talk about today, or like the main punchline for us, is not just this equivalence between soft theorems and ward identities for these asymptotic symmetries, but the fact that then they're naturally recast in terms of 2D conformal field theory ward identities. And so the objects that like I care about, we're studying recently, are these basically transformed amplitudes. So you're taking your standard S matrix element, which is a function of the fixed. So for massless particles, I would have like a on-shell momentum, so p squared is 0. So I can describe it by a direction on the night sky that it's pointing and an energy. And I take that object and I transform it into matter so that now it's designed to transform like a conformal correlator on the celestial sphere. So that's mechanic. I mean, like that's a matter of the basis transformation. But when you think about what you're doing there, so it's motivated by the fact that I want these symmetries that I was talking about in the previous slide to act in a way that looks like this CFT2 in 40. And so what I get out of that is I see that this transformed amplitude is like probe scattering at all energy scales. So from the point of view of someone who's like doing effective field theory, this is very anti-Wilsonian. So it could be taken as a bad thing, but the plus of it is that basically if you can really use these symmetries to your full advantage and see that there should be consistency conditions when I look at scattering across energy scales, then that could be quite powerful. So for the celestial holographers, this is a plus, and we're pushing that direction actively. So what the punchline here, I guess, is like, or the point of the title of the talk, is the way in which different scattering features get encoded into CFT structures. And these structures are highly constrained by the symmetries, and so that's the point of doing so. So in the infrared limit, we started with this notion of soft theorems giving me symmetries, asymptotic symmetries in the case of the 4D interpretation. Well, in 2D, these become different currents. You get certain null state conditions, so differential equations that your amplitudes have to satisfy because of the nature of the factorizations that occur. And those special conformal dimensions that happen there are basically guaranteed by the representation theory of the 2D CFT. And it also gives some insight into dressings because those become these like low energy modes that have very simple toy models in this 2D picture. When it comes to collinear limits, you have now this operator product expansion that you're basically trying to, you can match onto. And the fun thing about that is that basically these symmetries will actually constrain, you can somewhat derive the coefficients you would otherwise get by taking the Park-Taylor formula or other beyond Park-Taylor amplitudes and just trying to manually, like you can try to match it on both sides, but the fun thing is you can use symmetries to derive those OPE coefficients, which is fun. And then also pushing the conformal block decomposition, perfect, yeah. Pushing the conformal block decomposition, basically instead of like your amplitudes have more symmetries than would be obvious if you just do everything in perturbation theory. So the more the different framework, a different framework is a good thing. If you can try to find a way to break down, like instead of if you have a full understanding of the spectrum of the operators that can appear in channels in this conformal block decomposition picture of it, as opposed to having to do like the Feynman diagram perturbations, that would also be useful. And so there's another active route. And then the ultraviolet, the fact that this transform even converges corresponds to the fact that you want the amplitudes to be damped in the UV, which is string theorists love because that's what you get this ultra soft behavior there. And the way that you then look at behavior in the conformal dimension that you're transforming to as opposed to frequencies lets you kind of take a step back and kind of look at the consistent scattering from that picture. So this is the punchline there. And so that just gets me to my closing remarks, basically, is the whole point of this map was to find a way to then use CFT techniques to learn about amplitudes. So you're using these symmetries to motivate going to a basis for scattering where then you're trying to then find general statements that you can make in that basis because you're taking advantage of these symmetries, which can then come back and teach you about amplitudes. So I gave a little bit of a taste because it's a short enough talk of the things that we're learning. It's a very active, like under development field. So what we have right now is the following. We have these symmetries that are enhancements that are made manifest now. We've reorganized soft and collinear limits, so that's relatively well understood. And we know that we're basically probing both the deep IR and the UV, and we have some idea of what consistency conditions we can impose on the, so analyticity in this delta corresponds to somehow this damping in the UV. So like we have this nice dictionary that we're building up. And so the step forward are really to expand this dictionary. You want to connect to adjacent subfields and finally find an intrinsic construction for this guy. And ideally there, like if you, it's kind of pushing in kind of one direction at the moment, which is like looking for this dual and mapping from the bulk Minkowski space scattering to the boundary. But instead, once you have like all of the consistency conditions, the data that you need to have in this conformal field theory, you can go backwards or just try to do like a classification program intrinsically in this 2D guy and see what you can say then about amplitudes. So there's a lot of subfields that are kind of feeding into it. I talked about, for a lot of this talk, the motivation from this asymptotic symmetry soft theorem story into it. And of course, on the asymptotic symmetry side, that's connected tangentially to like gravitational wave astronomy. Are you going to see these memory effects and kind of validate that like the asymptotically flat approximation is good at the scales that you're seeing in those contexts? And then also on the soft theorem side, these reparameterization and variance symmetries match some things from Jet Fino. But in the end, right, we're trying to learn about amplitudes from these other techniques. So that's the point. And so did I get through anything that I was promising at the beginning? So from the first question, which is what are the fundamental laws of wave by nature? Well, at least we have some new symmetries that should also be observed. What happens when I fall into a black hole? Well, those symmetries should constrain that problem. So that's a plus there. And then what happens at scales that we can't yet probe? Well, at least we have a framework that basically is sensitive to the UV. So hopefully we can have something fun to report there soon. And that's where I'm at. So thank you guys so much for your time. And I think that's my 25.
Thank you very much for your very broad and far-reaching talk. I see appreciations and one question. Decker.
So thank you, Sabrina, for a great talk and for such wonderful slides also, by the way. So I missed a crucial step, and I hope maybe you could fill it in. So I understood as you went to these celestial amplitudes why you were investigating symmetries of the low energy theory.
Yeah.
But how did you get UV information out of it? I didn't quite follow that part.
So the issue is that you're starting from the IR to build up the framework for that. Okay, now you have this amplitude, and I'm saying that if I want to write it as a correlator, I need to integrate over all energy scales with certain weights. So I'm taking this integral transform here. So literally from the point of view of saying that I want this transform to converge, I need the energy behavior to be such that it lets it happen. So there's nothing a priori coming in about like the UV has to make sense. Like for instance, I can make sense of it as a distribution in delta if I want to say just like transform the tree level graviton amplitude. The scaling is such that this guy doesn't converge but formally can be made sense of. So the kind of power that you get is that, okay, in this basis, I'm going to say, well, it has to be analytic in delta. Like that's an assumption that you make. And that type of assumption maybe seems natural from the point of view of someone studying these like objects with the just defined on the left-hand side, oh, my variables are z bar and delta for each particle. And so the claim is that, which is slightly interesting, is that if you try to make kind of innocent assumptions on the one hand side, it says something kind of strong about the UV on the other side. And so there's a beautiful paper by Nima Arkhani-Hamid, Andy, and then Pate and Ray Clario exploring that, and it's also been explored since. And so there, it's not that the frame.
Oh, may have lost her.
Yeah, I think we have, or at least it's frozen. Oh, she's back.
Okay, good. Sorry. So the upshot of it was just that the assumptions that you can make once you're in that basis lead to interesting constraints on high energy scattering that you might then also want to say are natural.
Thank you.
Yeah.
If I may, we have a question in the chat.
Yes.
Somebody is asking, how does this framework handle singularities in the context of black holes?
Yeah, so there, I think it's still active in the sense that, so what we would normally think of is basically there'd be an extra degree of freedom for the, like you chop out the horizon and essentially think of that as another boundary component. So right now I haven't gone into too much detail with it, like what I'm meaning by these plus or minus, but essentially the structure of the boundary of space-time is such that I have like an incoming, like set of particles, outgoing set of particles labeled by these plus or minus. And then if I had a horizon, I would also have like a label for that. So for instance, the modes that I was suggesting were interesting from the point of these toy models in the infrared. Those dressings have contributions from each of those boundary components. So in that case, the singularity is still behind the horizon at the stage that I'm talking about. And the like you basically have now this extra degree of freedom coming from that boundary, from this infinity description. But then of course that guy has to evaporate. And so the fact that I guess like I haven't, from the point of view of the celestial CFT, we haven't quite like mapped that together. But from the point of view of just like the zero modes, for instance, you can see that somehow the radiation in the outstate should reflect like kind of like the fact that you're like not sensitive to measuring that is why you see like this thermal state. And that's some of the papers by like Strominger and Hawking and Perry, we were looking into that. And then with Herman Verlinde, we were looking at how the tying of the dressing at both of the boundaries says something about the infaller, essentially kind of making a measurement of some of these soft modes when they fall through. So that, like what I'm saying there is I'm saying that we have an understanding of the ingredients that go into the soft modes in that interesting context, but it hasn't been like at the same level of ADS CFT, say, where like you would have a system where you know the state at the boundary and then like that it's unitarily evolving and what's happening when you evaporate in the bulk. So like there's room to grow there, but we do have some sense of the ingredients that would happen.
Thank you very much for answering the last few questions and for the great talk and great illustrations that you gave us. So I would like at this point to call for Tao Han, who would like to share a few words with all the participants. Tao, you're on.